for the Extreme Universe collaboration, the 22nd Colloquium. And today we have Masayuki Hashisaka, professor from ISSP, the University of Tokyo. And the title is Electron Dynamics at Boundaries of Quantum Many-Body Systems. And if you could have a question, just unmute yourself and raise your hand or speak up. Okay, please, let's talk about so.
Yeah, thank you very much. First of all, I would like to thank the organizers for giving me this opportunity. And I would also like to thank this beautiful poster. Actually, this is the most beautiful poster I have appeared on. So thank you very much. So I would like to, oh, sorry. Oh, it doesn't work. Oh, okay. So I'd like to start my talk from myself, brief self-introduction. So I'm an experimentalist on condensed matter physics, and my research field is particularly called mesoscopic physics, and it has the keywords of quantum Hall effect or topological materials and quantum point contact and something like that. And some of these keywords will appear in today's talk. And looking at my own history as a researcher, I spent student days in Kyoto University, particularly for my master course and PhD course. I studied at the Institute for Chemical Research in Professor Ono's group. And at that time, my supervisor was Professor Kobayashi, and he's now the professor at the University of Tokyo. And after finishing my PhD, I moved to the Tokyo Tech as an assistant professor in Professor Fujisawa's group, and started the quantum Hall, the studies for quantum Hall physics. And then I moved, after 7 or 5 years, I moved to a private company, NTT. This is a big telecommunication company in Japan, and NTT has very nice fundamental research institutes, and I belong to one of these institutes in their group, and continued the condensed matter physics research and experiments. And last April, I moved to ISSP, the current position, and now I'm starting to build my own group. So I'm a very new person in the present place. So I'm trying to continue this condensed matter physics research at the present situation. Yeah, okay, I move on to the physics part. So I want to start this talk from a very basic concept of the experiment. So suppose that I have one material, and this is a sample, and I want to know the bulk properties of this sample. So in that case, I may apply some action to this material or the sample and measure the reaction from this sample. And this reaction always comes through the boundary and reflects the mismatch between the bulk property of the sample and the outside world. So that is basically written within the single particle picture. So if there's a mismatch, we can run something from the reaction through the boundary. And that is the measurement I will discuss today. And one very fundamental example is photonic optical experiment. So if I want to know the refractive index of my sample, I may apply incident light to the surface and measure the reflected light. And thanks to the Fresnel's law, I can know the refractive index from the reaction through the boundary of this material. And this kind of experimental setup is the one I will continue to think through this talk. And the target of my experiment is the quantum many-body systems. So I think the best example is the Andreev reflection at a superconductor junction. So as you know, superconductor is a very well-known quantum many-body system. and it has Cooper pairs inside as charge carriers. And of course, this Cooper pair is very different from the charge carriers in single particle pictures. So their electrons are holes. So because of the mismatch between the Cooper pair and these charge carriers, I can expect some signals of the bulk property from the reaction through the boundary of this system. So in the in the view from the viewpoint of the charge conservation, so if we inject one electron to the boundary, I can expect that the current traveling through the superconductor is carried by the Cooper pair. So to conserve the total amount of charge during this process, we can expect to observe the back reflection of a hole from this boundary. So this is the boundary reflection, and actually this is the fundamental concept I want to discuss in this talk. So what is the my target quantum many-body systems something like this. So we know there are several quantum many-body effects. Of course, superconductivity and also fractional quantum Hall effect, tomorrow liquid behaviors, or Kondo effect is another very nice example, and probably there are many others. And in this talk, I will discuss the focus on the fractional quantum Hall's effect and the tomorrow liquid nature, and both of them can be observed in quantum Hall systems. And if we think about the electron dynamics of these quantum many-body systems, we can expect some analogies between these quantum many-body effects with and the superconductivity, because there's of course all of these quantum many-body systems has bulk properties different from the single particle picture. So if we think about the electron dynamics or electron scattering at the boundary, the reaction from the boundary should reflect the bulk properties, reflecting the electron correlation in the bulk quantum many-body systems. So that is the analogies I want to discuss. And another good thing is that by looking at, by focusing on these analogies, we can probably understand the difference between these different quantum many-body systems. Of course, these many-body systems are very different to each other. So by comparing these systems, having the analogies in our mind, then probably we can clarify the difference from the comparison. That is the concept I want to discuss today. So in the rest, I will first talk about the quantum many-body effects in quantum Hall systems. They are a fractional quantum Hall effect and the tomorrow nature behavior of edge channels. So this is a very famous picture for the two-dimensional topological systems. So this picture shows quantum Hall effect and quantum spin Hall and quantum anomalous Hall effects. And of course, the quantum Hall effect is the biggest brother of these three. And their quantum Hall effect has integer and fractional quantum Hall effects. And both integer and fractional quantum Hall effects are celebrated by the Nobel Prizes in 1980s and 1990s. And the first one, the integer quantum Hall effect, discovered by Klaus von Kritzing, is basically can be understood within the single particle picture. So it is based on the cyclotron motion of an electron and the Anderson localization of these electrons. So if we think about the elementary excitation of such a system, the excitation should be an electron, and therefore the charge carrier should have the elementary charge E, and the quantum fraction fermionic quantum statistics with statistical angle of pi phase. And on the other hand, fractional quantum Hall effect is known as a result of quantum many-body effect inside. So for example, in the case of Laflin state at filling factor 1/3, this system have quasi-particles with carrier charges of E/3, so it is smaller than the elementary charge. And this quasi-particle can have non-fermionic and non-bosonic quantum statistics. It is sometimes called anyonic statistics. And in the case of 1/3 filling factor, it can be fractional phase, pi-3 fractional phase should be observed by the braiding processes in the system. So these very exotic nature of fractional quasi-particles are very nice demonstration of the correlation effect in the fractional quantum Hall effect. So this is a simple schematic of the fractional quantum Hall state. And so this picture looks quite similar to integer quantum Hall state. So the fractional quantum Hall state effect appears in the two-dimensional electron systems. Sometimes it is in a semiconductor heterostructure. And when we apply a very strong perpendicular magnetic field to the two-dimensional electron gas, then the fractional quantum Hall state appears. And if you look at the bulk properties, so it is incompressible. In other words, it is insulated for electron transport because the system is energy gapped, has energy gap inside. And the electron transport is possible only along the edge of the sample. This is called edge state of the fractional quantum Hall state. So this simple schematic looks quite similar to that of the integer quantum Hall state. And the electron, the signatures of electron correlation can be checked by taking a closer look at the bulk properties. For example, in the case of filling factor 1/3, we can expect this such a ground state inside. So in the 1/3 state, the strength of the magnetic field is something like that. So we can expect 3 flux quanta for a single for one electron. So this is the strength at the filling factor, strength of the magnetic field at filling factor 1/3. And fractional quantum Hall effect occurs because of the repulsive Coulomb interaction between them. So electrons tries to far apart from each other. And because of this repulsive interaction, electron tries to occupy the area, exactly the area of 3 flux quanta. So in the fractional quantum Hall state, the electron density of the system becomes very uniform. And because of this Coulomb interaction effect, the system can decrease the total energy of the system and by opening the gap, energy gap of the system. And what is the minimal excitation in this system is it's called elementary excitation, and this is the not the adding or removing an electron, but adding or removing a flux quantum. So if we add or remove a flux quantum, because one electron occupies the area of 3 flux quanta, the flux should have the charge modulation of E/3. So this is the fractional charge of this excitation. And because this this modulation causes a very localized excitation in the electron density, so it is called a quasi-particle. So it is a particle-like excitation in the system. And if we look at the quantum statistics of these quasi-particles, we should observe the fractional charge of fractional phase of the statistical angle. So this fractional quasi-particle is a good signature of the quantum many-body nature of the fractional quantum Hall state. And another important quantum many-body effect is the appears in edge channels. So both integer and fractional quantum Hall systems have their edge states at the sample boundary. And because of the one-dimensional nature of these electronic state, they show the quantum many-body behaviors. They are called Tomonaga-Rattinger liquids. And comparing with the Fermi liquid picture of two-dimensional or three-dimensional systems, so in the Fermi, they're called Fermi liquids. One charge excitation by adding for example, by adding an electron to the system causes a very localized excitation in the 2D or three-dimensional systems, and the correlation function in this system becomes very local because of the strong screening by the surrounding electrons. But in the case of one-dimensional systems, one charge excitation cannot be screened very strongly in one-dimensional systems. So the correlation function becomes very long range and decays only following the power law. So the excitations behaves as a wavy dynamics of this one-dimensional electron system. And this is the Tomonaga-Rattinger nature of the edge channels. And the Rattinger natures of the edge channels have been studied intensively for the fractional quantum Hall edges by measuring the power of behaviors from the 1990s. And in this picture, the theorists have considered the short-range contact interaction inside the 1D channels. And this is, of course, okay and very nice Rattinger nature of edge channels. But on the other hand, integer quantum Hall edge channels has been considered as non-interacting one-dimensional systems. So they are not considered as Tomonaga-Rattinger liquids. This is because they considered only the short-range interaction. But in reality, in real devices, of course, there are long-range Coulomb interaction. So if we take this long-range Coulomb interaction into account, integer quantum Hall edge channels sometimes show Rattinger liquid behaviors like charge fractionalization or spin charge separation. That is a very famous behavior of the Rattinger liquid. And because the long-range Coulomb interaction can be artificially screened by or designed or controlled by using the metal structures surrounding the one-dimensional system, we sometimes call such a system an artificial Rattinger liquid. And I will talk about this later. So thus, I explained the quantum many-body effects that appears in quantum Hall systems. So in the rest, I will talk about the electron dynamics at the boundaries of these quantum many-body systems in the quantum Hall state. So again, I mentioned about the reflection of the superconducting junction. So this is a most fundamental and famous electron scattering process at the boundary of quantum many-body state. So I would like to discuss the electron dynamics at the fractional quantum Hall effect and the Tomonaga-Rattinger liquid with comparing by comparing with these dynamics with the reflection, the superconducting junction. So first, I will talk about the junction of fractional and integer quantum Hall systems. And at this junction, we can observe the reflection-like charge scattering process. And the contents of this talk in this part is described in this paper. And they are my collaborators for this work. So when I first considered the junction of fractional and integer quantum Hall systems, I thought about the charge conservation during the charge scattering process at the boundary. So because the fractional quantum Hall state has host the fractional quasi-particles with fractional charges, carrying fractional charges. So if we inject one fractional quasi-particle to the boundary of the fractional and normal state, then an electron needs to be excited in the normal metal side to transmit the current. So because of the charge conservation, maybe we can expect the back reflection of quasi-Hall from this boundary in this process. This was my first thought for this system, and we tried to check the theoretical papers discussing this kind of phenomena, and found some theoretical papers. So these papers, and all these papers discussed the tunnel couplings between the Lagrange liquids of filling factor 1/3 and non-interacting one-dimensional system. This is the edge of the filling factor 1 integer quantum Hall state. And in this system, the tunneling current through this junction can be analytically solved by transforming the basis of the system to this setup, 1/2 and 1/2 junction. And the theories tells that in the strong coupling limit of this gamma, so infinitely large gamma, then the conductance, electrical conductance through this junction should be 1/2, because the system is 1/2 integer, 1/2 edge state. So this is okay. This is an analytical result. So I believe this calculation, prediction. But if we go take a look at the original setup, this prediction is very exotic, because the system is formed based on the 1/3 fractional quantum Hall state. So the conductance of the 1/3 h should be 1/3 times e squared by h. So this half e squared by h conductance means that the electrical current injected to the 1/3 channel is enhanced at this gamma to transmit the charge current to the filling factor 1 side. So because of the charge conservation, we can expect the back reflection of negative current from this tunnel current. So this is a very, this seems very exotic process at this junction. And one theory gave the physical interpretation for this enhancement of the current. So that is the under reflection of fractional quasi-particles discussed in this paper. So they claim that this enhancement of the current can be understood as the Andreev type reflection of fractional quasi-particles to generate an electron transmitted through the junction. And because two of quasi-particles form a single electron, one quasi-Hall is back reflected from this junction. And this is the interpretation they gave in this paper. And I thought that these predictions and interpretations are very interesting. So try to observe in experiments for the first time. So we prepared a sample of 1/3 and 1 junction using a standard conventional semiconductor heterostructure device. So we prepared a 2-dimensional electron system in a gallium arsenide-based quantum well system. And this is a micrograph of our device. And the electrons are confined in blue and red regions. And we applied a perpendicular magnetic field to form the filling factor 1 integer quantum Hall state in this. And additionally, we applied a negative gate voltage to this red region to decrease the electron density in this region. And in addition, we applied a strong negative gate voltage to the yellow gates to deplete the 2-dimensional electron system underneath. And this is a magnified view of this area. So at the center of this whole bar device, we can have the point-like junction between the 1/3 fractional quantum Hall state and filling factor 1 integer quantum Hall state. And this is our device. And when we set the voltmeters and the ammeter and the voltage source, something like this, we can perform this experiment according to the Landau-Whittaker edge transport picture. So we can directly measure the conductance through this junction by applying the source drain bias and measuring the current or measuring the voltages in this system. Voltages of the edge channels toward and coming back from the boundary. And before going to the experimental results, I would like to discuss the electronic state near the microscopic electronic state near the boundary. So to take a look at this boundary, let us think about the cross section of this boundary. So this is the cross section. So our two-dimensional system is below the surface, something like this. And we apply the negative gate voltage to the on the left hand side to decrease the electron density and form the filling factor 1/3 state. And on the right hand side, we have the filling factor 1 state. So the question is how this electron density changes from this 1/3 side and to the filling factor 1 side. And the naive intuitive picture of this electron density profiles might be something like this. So on the left, we have 1/3, right? We have filling factor 1, and they might be smoothly connected to each other. But as I wrote here, this naive picture is wrong. So to obtain the correct structure of the electron density profile, we need to consider the effect of electron correlation in the fractional quantum Hall state. So if we take this correlation into account using the density matrix renormalization group calculation, and we obtain this electron density profile. This was done by Ito-san and Shibata sensei in Tohoku University. So because 1/3 state is a very has very uniform electron density because of the gap opening, and because this gap opening is results from the ratio of the number of electrons and flux quanta it's 1 and 3. So if near the boundary, the electron density changes, so the energy gap of the fractional quantum Hall state actually needs to be closed. So the fractional quantum Hall effect becomes very unstable at the boundary. So this oscillation shows the instability of the fractional quantum Hall state. And we always observe the complete depletion of the two-dimensional quantum system at the boundary to touch the filling factor 0. And then through this depleted region, the 1/3 state can be connected to the filling factor 1 integer quantum Hall state. So here we see the counter-propagating 1/3 edge and filling factor 1 edge. So if I show you the schematic of our junction device, so this should have this kind of electron density profile. So on the left-hand side, we have 1/3 region, and right-hand side, we have filling factor 1 region, and they are connected via the point-like junction formed by the split gate voltages. And even if the two systems are very close to each other, there appears the depleted region between the 1/3 and one system due to the electron correlation in the fractional quantum Hall system. So this mechanism. So here, in this junction, we always have the filling factor 1/3 edge here and filling factor 1 edge, and they are connected to each other through the tunnel couplings between them. So if we measure the current flowing from this side to that side, that should be carried by the tunneling coupling, something like this, as considered in the early theoretical papers. So our device is exactly suitable for checking the theoretical predictions, discussing the Andreev type reflection of fractional quasi-particles. So now I show you the experimental result. So this is a simple experiment. So we just applied charge current from the one side, and measure the transmitted current. And this is the result. Plotted as a conductance of the junction as a function of the split gate voltage. So these voltages. So when the junction is very wide, we always observe the conductance 1/3. So this reflects the conductance of the bulk 1/3 state. But when the narrow junction is formed at negative gate voltage, the conductance start to fluctuate, and it sometimes overshoot the 1/3 conductance, something like this. And this overshoot is the signature of the exotic enhancement of the tunneling current. So that is the that can be interpreted as the Andreev type reflection of fractional quasi-particles. So this is the first evidence of the Andreev processes in the fractional quantum Hall state. And another evidence is also obtained by measuring the reflected current. So this is a signal from the reflected side as a function of the split gate voltage. So when the junction is wide, again, we observe the zero signal from this reflected side. This means that all the injected current is transmitted through the junction. But when the narrow junction is formed, the signal start to fluctuate and sometimes shows a negative output from this junction. So this actually corresponds to the quasi-Hall reflection from this boundary. So this is another evidence of the Andreev processes. And the fluctuation of the signals in this and that experiment result from the multiple scatterings at this junction. So in this device, of course, we first tried to form the single tunneling couplings between the two systems, but in reality, our junction device had many scattering centers between the counter-propagating channels. And in such a case, theories predicted that the conductance fluctuates between 0 and 1/2. It's 1.5 times larger than 1/3. And so our observation, this data completely, I think, completely correspond to the theoretical predictions for the multiple impurity cases. But anyway, our experiment is was the first observation of the Andreev-like processes. And I would like to note that recent experiment succeeded in forming a singular impurity between the two fractional and integer systems using a graphene device. And this was appeared from Andrea Young's group last year and appeared in Science. So these theories are completely observed, demonstrated in the experiments. So in summary, this is a summary of the first topic. So we have observed the Andreev reflection-like charge scattering at the fractional quantum Hall boundary. So this is a strong. I think this is a strong analogy with a superconducting device, and the observed conductance and the fluctuating nature of the conductance shows the and emphasizes the difference from the superconducting device and the fractional quantum Hall device. So we can see both analogies and differences between the superconductivity and the fractional quantum Hall effect. So that is a summary of the first topic. So, okay, can I, okay, if you don't have any questions, I want to go ahead. So, Okay, I go ahead. So I will explain the second example of the electron dynamics at the boundary of the quantum many body effect. And this experiment was explained in this paper in 2017, and they are my collaborators for this work. So before going to to this experiment, I want to mention about the Cooper pair splitting in the superconducting junction again. So Cooper pair splitting is one type of reflection. So this is a schematic of the Cooper pair splitting. So because a charge carrier in a superconductor is a Cooper pair, when we pick up current or charge from the superconductor, the Cooper pair splits into the two electrons. But in the S-wave superconductor, it's their spin up and spin down electrons, and they are entangled to each other. So if we prepare this kind of Y-shaped junction in the normal metal side, probably we can split this Cooper pair into the left to the left and right leads of the normal metals, and we can generate the quantum entanglement between the split electrons in these two leads. And this Cooper pair splitting has been actually intensively studied in mesoscopic physics. For example, in these papers, as a promising device for generating pairwise entangled electrons in solids. And I would like to think about the analogy of the electron dynamics at the boundary of tomorrow-Latinger liquid with this Cooper pair splitting. And usually the electron dynamics at the Latinger liquid is discussed in the context with the keyword of electron fractionalization or spin charge separation. But from my point of view, these processes are analogies with the Cooper pair splitting, and that is my thought. So again, I show you this famous picture of the 2D-dimensional topological systems. So all these 2D-dimensional topological systems have edge states at the sample boundary. And in these pictures, these edge states are drawn something as non-interacting one-dimensional systems. But as I mentioned before, if we are taking the long-range interaction into account, we can sometimes observe the Latinger nature of the edge state, particularly in the RF gigahertz transport properties of the system. So I want to, as a background, I want to explain about the gigahertz electron dynamics at the quantum Hall edges. So usually the quantum Hall systems have a very large energy gap in the bulk, and thus this gap has usually higher than 100 gigahertz. So it is difficult to directly excite some RF excitations by applying the gigahertz signals to the system. And what RF signal can do to the quantum Hall system is to excite some edge excitations, because edge is a gapless one-dimensional electronic state. And such edge excitations have been discussed with the keyword of edge magnet plasmon. This is understood as a spatial charge modulation, spatial modulation of the boundary of the two-dimensional electron system, the integer quantum Hall system. And this edge magnet plasmon transport has been historically discussed using the hydrodynamic approach for the charged electrons in the integer quantum Hall systems. And this edge magnet plasmon transport can be modeled in a more simple setup, theoretical setup, using a circuit representation. So in the hydrodynamic approach, we need to solve the three-dimensional Poisson equation or something like that. So it is quite complicated to predict what will happen in the real device of the integer quantum Hall system. But if we simplify the edge dynamics using this circuit representation, we can easily expect what we can do using the RF excitations, RF signals applied to the integer quantum Hall systems. So in this representation, we replace these hydrodynamic equations by these simple one-dimensional equations. And if we perform this this replacement, we can consider or better understand the effect of inter-channel Coulomb interaction. So as an example, I discuss the case of co-propagating edge channels. For example, in integer quantum Hall state, field factor 2. Then we can replace the Coulomb interaction between the edges by express the interaction between the edges by the capacitive couplings between the channels. And by using this circuit representation, we can derive the one-dimensional wave equation along this edge channel. So that is this. So here we have low up and low down, and low up and low down are charge excitations in these channels, up and down channels, and they are coupled to each other through this matrix element UX. And all these matrix elements are the function of these capacitances in the system. And the eigenmodes of this system can be obtained by diagonalizing this interaction matrix. And in the case of co-propagating channels, we find that the elementary excitations in this system, they are the charge excitation having the same amount of charges in both channels, and the spin mode. This is charge excitations with opposite signs. So they don't this doesn't carry any charge, but carries the spin degree of freedom. This is the eigenmode of this system. And this representation is about the classical hydrodynamic motion of the 1D edge channels. But this can be understood, simply applied to the quantum mechanical nature of the transport phenomena in quantum Hall systems. And this was discussed in this theory paper. And in this paper, these theories discussed that the a single electron injected to the integer quantum Hall system can be, for example, fractionalized by injecting this electron into the interacting edges. And this is an eigenmode in this case. And to form this interaction mode in this central region, the small amount of charge is back reflected from this boundary to fulfill the charge conservation during the scattering process. And this is called charge fractionalization, but of course this is understood as a under reflection like charge scattering process in the terminal liquid boundary. And another example is the spin charge separation, which I will talk a little bit more in the rest. So when we inject one electron to the spin up channel, so this spin up electron is not the eigenmode of or elementary excitation of this coupled system. So this spin up electron is a sum of the charge mode and the spin mode. So and because of the difference in their propagation speed, they are split into the two as a local charge excitation of the spin excitations, as depicted in this figure. So in the rest I will talk about the experiment observing this spin charge separation. So this is a device we used for observing the spin charge separation. So the device is a little bit complicated, but this is a two-dimensional electron gas in a semiconductor conventional device, heterostructure device. And we prepared these yellow and green gates and prepared several measurement instruments for applying some pulse and measure some current output from the system. But this is a little bit complicated, so I used this schematic for understanding, for explaining our experiment. So in this setup, we apply the voltage pulse to excite a charge pulse, non-polarized charge pulse to the cooperating state channel. And we inject this non-polarized charge to the spin filter here to inject only the spin up component of this charge pulse to the interacting target channels. So this is our terminal lattice liquid. So this spin filter at the input is forms the boundary of the terminal lattice liquid of this target lattice liquid, and this spin up charge injected to the system is the that's actually the mixture of the charge mode and the spin mode. And they spatially separated after the propagation, after some time, because of the difference in their speeds, and reaches the second spin filter. And this second spin filter transmits only the spin up component of these two eigenmodes, and to bring the spin up component to the time resolved charge detector. And this is in the signal. So as a function of the time of flight in this pump and probe measurement. And the vertical axis is charge current observed in this detector. And we clearly see the two peaks of the signal. So we applied only one charge pulse, but obtained two separated pulses, and this is a strong signature of the separation of these two modes. And if we inject the spin down charge to the target system, we observe that the sign of the second pulse is reversed. So we can see that the second peak is second signal is a spin mode, and the first one is a charge mode. So these two experiments clearly demonstrate that at the boundary of this terminal lattice liquid, an electron excitation, charge excitation, is transformed to the eigenmodes of the two terminal lattice liquid, and they are spatially separated and observed as the two different signals in the system. So I would like to summarize the second part. So in our experiment, we injected single electrons of spin up or spin down charge, and from at the boundary, these excitations are transformed to the charge mode and spin mode, and spatially separated due to the fractionalization process. And this is an analogy of the Cooper pair splitting. So the eigenmode of the system in the superconductor is a Cooper pair, but if we take this Cooper pair to the outside of the system of the superconductor, they are split into two electrons as shown in this Y-shaped picture. So this is the analogy of these two systems. But of course, we again observe the strong difference between the two systems, two processes. So I think it is nice to compare to this. I think it is nice to discuss this spin charge separation process in the context of the analogy to the electron dynamics at the boundary of the superconductor. So in summary, this is a summary of the whole of my talk. So I discussed that the take-home message of my talk is that electron dynamics at the boundary of the quantum many-body systems show several analogies between different quantum many-body systems. And by comparing these systems, we can, of course, pick up the difference of the different quantum many-body systems. So discuss this kind of comparison between different electron dynamics. So that's all of my talk. And if you have questions, I want to accept questions from you.
Thank you, Professor Hashisaka. And now the session is open for questions.
So can I ask a very elementary question?
Yes.
So, I'm not the expert, so I have some basic question about your first part. And so you talked about this conductance, and you know the 1.5 times E square over 3. So
Yes.
how this 1.5 appears in your scenario?
Yeah. So, but this is a theoretical analysis, but the 1/3 state and one state, the tunneling problem between the 1/3 and one systems can be transformed to this 1/2 and one system, tunneling between the 1/2 and 1/2 systems. This is understood using the bosonization of the excitations in this setup. And because the tunneling, this problem is equivalent to this problem, if we think about the infinitely large gamma, tunneling coupling gamma, the conductance, the transmission should be perfect between the 1/2 and 1/2 systems. So in that case, we should observe the conductance of the whole device to be 1/2 times E square over H, and E square over H is the 1/2 is the quantized conductance of the Lagrange parameter 1 H state. So that is 1/2, and 1/2 is 1.5 times larger than 1/3. So the 1.5 comes from the
I see.
difference between
I see. Yeah, because it's 1/3 is somehow basic unit of this. Quasi-particle anyons.
Yes.
So I'm really surprised that you have a 1.5. I mean, like you're cutting the elementary excitation into half and multiply 3. So, but this is it's come from quantum analysis of this bosonization.
Yes. So, if we calculate the conductance using the bosonization technique, so this conductance, the value of this conductance is understood as a tunneling current between this 1/2 and 1/2.
Thank you very much. It's very interesting. Also, thank you very much for very clear presentation.
Thank you very much for your comment.
Very interesting experience.
Any other questions? Please.
Okay, thank you very much for your very interesting talk. So for the experimental results for the first part of the experiment, so your plot shows many oscillations.
Yes.
And you have explained that they are due to the multiple impurities.
Yes.
So is it difficult to know about the configuration of the multiple impurities? So it would be some inverse problem. Is it difficult?
Yeah. But if I directly answer your question, it's difficult to distinguish the what kind of scatterings are present in our device. But your question is strongly related to the things I prepared in the appendix. I think I don't have enough time to discuss this, but the situation we have is something like this. So we have the counter propagating one third and one channels, and they are interacting through the Coulomb interaction. And there we have a lot of tunneling couplings between them.
Yes.
So this is a setup, our setup. And in this case, there are many theories about this setup. And the theories discussed that this setup should have this phase diagram of one-dimensional edge state. So as a function of the strength of the interaction between them and the number of tunneling coupling between them. And because of these two components, and because the system is Lagrangian liquid, the interaction strengths and tunneling coupling strengths are related to each other. And because of these two components, the correlation between these two amounts, physical characteristics, they show the strong coupling phase and weak coupling phase. And the conductance fluctuation we observed is the signature of the strong coupling phase. So this means that because of the renormalization of the Coulomb interaction to the by the tunneling couplings, we can say that there are actually many multiple tunneling couplings actually present with the Coulomb interaction, and we can say that the conductance fluctuation is a result of the interference between the many tunneling couplings, and so that is a mesoscopic fluctuation in the coherent disordered system. So that is the I think the answer. So this is a little bit complicated, but
Okay, thank you. May I ask another question?
yes.
So in the other experimental groups experiment, they realized just a single coupling.
Yes.
But even in that case, the conductance didn't go as high as 1.5 times E square over 3H, according to your slides, right? So it was like 1.2. The peak height was.
In our case, we observed the highest conductance of about 1.2, but theoretically it can go up to 1.5.
Okay.
Theoretically.
Yeah.
But in our device, we have a lot of impurities, and we cannot tune the coupling strength of them freely. So eventually we didn't observe the 1.5. But in the recent experiments by these people, they prepared the single impurity, and they can tune the coupling strength of that impurity because it is only one. So by increasing the temperature or applying the bias voltage to this, the tunneling coupling can be enhanced. The strength can be enhanced. So they in the limit they observed this 1.5.
Oh, I was just confused. Sorry. So I thought the right-hand side figure was not yours, but theirs.
This is mine. So sorry. This for this, and this is
yeah. Okay. Thank you. Thank you for your clarification.
Okay, any other questions? If not, it's more or less the time is up. So thank Hashisaka-san again for having a great talk.
Very much.